Okay, so in this video we have an integral from 0 to infinity of x divided by the hyperbolic cosine of x dx. So now the strategy we're going to be doing is we're actually going to be doing a couple of substitutions, then eventually transform it into a form of series, and then everything from there will come out nice. So you'll see why. And okay, let's get started. So first thing I want to do is let's actually convert or rewrite the hyperbolic cosine of x in its exponential form. So by definition, hyperbolic cosine of x is equal to e to the x plus e to the negative x divided by 2. So with that, I can just replace hyperbolic cosine with this exponential form. Under division, so I can actually just flip its reciprocal, so that way we have 0 to infinity of 2x divided by e to the x plus e to the negative x dx. Okay, there's a constant in here, so I can actually just move that outside, and then let's see, x, and then e to the x plus e to the negative x dx. Okay, now to preserve our inequality, what I'm actually going to do is multiply and divide e to the x. So this way, eventually, coming up, we'll actually be doing our substitution. So 0 to infinity, this is x times e to the x, and then divided by e to the x. So e to the x multiplied by its denominator. So this is e to the 2x, and then plus 1 dx. Okay. All right. Now let's actually do our substitution. So let u equals e to the x, and because there's an x in here and we want to substitute for that in terms of u, so let's actually solve for x. So I can actually take the natural log of both sides, so that way it yields ln of u is equal to x. And I can take its derivative, and I take the derivative of both sides. Du is equal to e to the x dx. And before we plug our pieces together, we actually need to change our bounds of integration, since everything will be in terms of u instead of x. So when x is equal to 0, then u is equal to 1. Or let me start with the numerator. Let me start with our upper bound first. So when u is equal to, or when x is equal to infinity, then u is equal to infinity. U approaches infinity, and then when x approaches 0, then u approaches 1. Okay, now let's plug everything back together with our substitution. Then we have 2 times, that means this is 1, this is infinity, x is ln of u, and then ex dx will cancel, and so e to the 2x we have in terms of u, that will just be u squared, then plus 1 du. Okay, nice. Now we're actually going to be doing another substitution. So this time I'm actually going to take the crazy approach, and we're actually going to let u equals 1 over t. Then dt is equal to negative 1 t squared dt. Okay. Now again, we need to change our bounds of integration. So now everything will be in terms of t. So that means when u approaches infinity. Okay. When u approaches infinity, that would have to mean, I wouldn't say t is equal to 0, otherwise that'd be defined, but rather to say t approaches 0. And then when u approaches 1, then that would have to mean t approaches 1. Okay. Now again, so 2 integral from, this time this is infinity, so this is 0 here, and then this is 1 here. Then I have ln of u, this will be ln of 1 over t, and then divided by u squared, so this will be substitute for 1 over t, so 1 over t squared plus 1 and then multiply or substitute our, that's actually supposed to be a du over here. Whoops. That's du. Okay, now du, substitute that for -1 divided by t squared dt. Okay, now let's actually simplify this out a bit. So -1 is a constant. I can move that outside, so that's -2. And we have our integration bounds where the smallest number is our upper bound and our bigger number is the lower bound. If we switch that, then that means it's multiplied by its negative, so that'll become a positive. But we also have that the natural log of 1 over t, it also can be rewritten in terms of with the base t, so ln of t raised to -1. When we use our natural log rules, we can actually move the -1 in front of the ln, and then it's also treated as a constant, so you can move that outside the integral, then that will be -2. So -2, 0 to 1 of ln of t, and then 1 over t, and then square that, so it's 1 over t squared. So multiply the t squared to here, that'll just be 1, and then t squared to here, so it's t squared. And you know, just for it, it's under commutativity under addition, so I just rearranged the terms. So now, this should be familiar to you. In a couple videos back, I actually computed the integral from the integral of the natural log of sine of x from 0 to pi over 4, and we have a very, very similar formulation. So what I'm going to do is we're actually going to this is actually can be rewritten as a geometric series. So this means this is -2 times the integral of 0 to 1 of the summation n equals 0 to infinity of -1 n, and then times t to the 2n multiplied by ln of t dt. Okay, then by using our summation rules, I can actually just move the constants outside and the summation symbol outside. So -2 summation from n is equals 0 to infinity of -1 to the n, and then the integral of 0 to 1 of 2tn t to the 2n, my bad, multiplied by ln of t dt. Okay. So now, everything from here is going to be simply doing integration by parts. Yes, this is exactly what we did from a couple videos back. So I'm actually going to use integration by parts to evaluate this integral in particular. So let u equals ln of t, and that means du is equal to 1 over t dt, and then let dv equals 2 raised to the 2n dt, then dv is equal to t to the 2n plus 1 divided by 2n plus 1. Okay, now integration by parts formula is u times v, then subtract from the integral of v times du. So let's start little by little. Let's actually evaluate u times v from 0 to 1. So when I multiply this together, so we have t to the 2n plus 1 ln of t, then divided by 2n plus 1. Okay, and then this is being evaluated from 0 to 1. Okay, so when t is equal to 1, notice that ln of t is actually just 0, so then the whole term just cancels to 0. Well, I wouldn't say cancel, it's just 0. And then when we evaluate t is equal to 0, then notice that when we plug 0 for t, it's always going to be 0, and then the whole expression itself just becomes 0. So this means this is 0. Okay, so far, now we have 0 minus then the integral of v times du, so we have t to the 2n plus 1 divided by 2n plus 1, then multiplied by 1 over t dt. We can actually cancel out since they share the same base of t, so that means this is negative, we'll write 0 to 1, we'll write 0 to 1 here, actually. Okay, then this will be t to the 2n divided by 2n plus 1 dt. Okay, then simple from here is just just your standard definite integral. Add 1, then divide by whatever's under the exponent. So this means this is t to the 2n plus 1 divided by 2n plus 1 squared. Then evaluate that from 0 to 1. Okay, so notice when we plug t is equal to 1, t is equal 1, then 1 raised to any number or any exponent generally, it's always going to equal 1. And notice that because our index starts at 0 and then it's goes to infinity, so it's all positive. So really, it's always going to equal 1. So that means we have, let's evaluate it at 0 also. So again, same argument from before. We plug t is equal to 0, then the base 0, any exponent of that is always going to be 0. Also be careful because 0 raised to the 0 is equal to 1, but because index n equals 0, so that means our index actually really for the exponent is 1, so it's still 0 regardless. So that means really this is negative 1 divided by 2n plus 1 squared. Okay, so now that we have that, 0 minus, okay, yep, so now let's just substitute this back in. So we have, that means negative 2 summation, and then multiply by negative 1, 2n plus 1 squared. Okay, so I could actually just factor out the negative 1, so that means the 2 will become a positive. So this is positive 2, and the summation of n equals 0 to negative 1 to the n, then divided by 2n plus 1 squared. And that's all we can do, but notice that this is actually, the series formulation is actually Catalan's constant, which we use when I've computed that integral of the natural log of sine of x way back. So I'm actually going to let c equals this Catalan's constant here, 0 n, and then 2n plus 1 squared. Okay, so now really it's basically we're done. We actually know for sure that this series converges by the alternating series test, but its convergence really cannot be represented in terms of fractions based on from its decimal expression, so we just have to leave it as it is. So really, we're actually done. So now the conclusion we can make is the integral from 0 to infinity of x divided by hyperbolic cosine of x dx is just equal to 2 times c, where c is our Catalan's constant over here. That's really nice, isn't it?